structure of today's session. Um, Suyash and Akash will be sharing. I will be sharing the platform with them accordingly after a while. But uh, in beginning, uh, in beginning, I will be talking more about kind of not about the very rigorously mathy part, but I will present some scenarios that just that will give you a few insights how where exactly Catalan numbers pop up in different um, real world or different scenarios. And again, English is not my first language, so um, if I get stumble upon while saying something, um, apologies for that in advance. Um, so I think we can start. So in the beginning, I would like to share scenario that many of you will be aware of. I'm sorry I can't turn on my video today, but yeah, but I hope you guys understand. Okay, in the beginning, I'll present you a scenario um, of a bank. In fact, we had them posted in our Facebook, but um, we had explained it in Nepali. So, and since we are having few audience from abroad also, so let me explain that to the rest of the members. Um, um, yeah. Sorry to make you guys wait. I just can't find the exact. Prashant, could you make me host so that I could use annotations in meantime as well? Thank you. Let me share my screen. Okay, so the scenario goes like this. Initially, we have a bank where people are queuing up either of the two purposes, which may be to deposit a sum or to withdraw some sum. The condition, uh, is that a bank does not, a bank cannot with a person cannot withdraw certain sum more than the bank has already. I mean, if bank has $20 and if somebody wants to withdraw $30, then that won't be feasible. I mean, digitally it could be, but this is a physical bank. So um, people are queuing up either to deposit money, and they could either borrow or deposit certain money. Initially, there are certain number of depositing people, say a number of people, each of them are depositing B, and we have C number of people who want to borrow money, and all of them want to borrow D dollars. And initially, say bank has E dollars. So in how many ways can we arrange these people in the queue so that bank is consistent at each of these transactions? Sorry. So what does it mean for a bank to be consistent? In fact, a bank won't be consistent when a bank has to borrow more than it has already. So this is I think this problem has not been solved up until now. I mean the general case where um, you know the bank has e-dollars, and all of the variables a b c d e and are unrelated. So but if we simplify the case uh, where a is equal to c, that is the number of people borrowing and deposit are same, and each of them want to borrow same sum, and initially bank does not have any money. So that will imply that the bank has to kind of has to have first people in the queue that will be depositing certain money, right? So how many ways are there? That's the problem where the Catalan numbers pops up. So I just want to make things clear again that if you guys have some question, you guys can always ask. Okay, so in this scenario that I presented right now, um, sorry, in this scenario that I presented right now, we have to arrange uh, people in the queue. All right, so I hope, does any of you are having any question?
I guess not. Continue.
Are you all familiar, like, are you okay with this case? So I will explain, I mean, we will explain how all of the cases, scenarios are related to Catalan numbers. This is just one of the cases. So another case where Catalan number comes in is where is where is like arranging the parentheses. Let's call it bracket in short. Okay. So let me turn on the video. I guess you guys can see. I don't know if it's much zoomed in, but I think it should work.
No, it's not.
Prashant, could you please highlight the?
You're the host.
Thank you. So this is
You're
a
the
very
host.
fairly simple. Yes, please.
You're the host. I cannot spotlight you. Make me the
Okay.
host.
Then I'll be making you host in a while. I'm sorry for making you wait. So the scenario goes like this. What you have to do is arrange. Suppose you have n pairs of brackets. Okay, n pairs of brackets. I think you guys have learned this earlier also in various classes or YouTube videos, but so but the question is how many ways can we arrange these four paired elements? One of like there are like this can be classified in two kinds. One is opening and the other one is closing bracket. So how many ways can you arrange these eight elements such that it is a valid arrangement? And what do I mean by a valid arrangement? It means that at any point the opening bracket is not more than is more than or equal to the closing bracket. For example, this is valid, but this and maybe like this will not be valid, because at this point we will be closing a bracket that has not been started. So this arrangement is not valid, but this arrangement is valid. So how many valid arrangements are there where are possible where sorry, how many arrangements are possible where these parentheses are validly arranged? This is the second scenario. There is one more scenario, in fact. Let me present that one. Sorry. So, So Prashant, could you please allow me to share the screen? Please don't make me host.
You can share the screen. Don't have to be the host.
Catalan number pops up is the Polygon triangulation. And what I mean by that is that, for example, you have a square or any quadrilateral, and you have to divide it into triangles. Okay, then how many ways are there to do so? Like while triangulating a polygon, the diagonals cannot cross over. Like there is a problem that where we draw all possible diagonals and we count the number of spaces. I guess there is a separate 3 blue 1 brown video dedicated to that topic, but what we are discussing, what we are interested here right now is to draw diagonals such that they don't cross over. That is, we are triangulating a polygon. So a triangle will just have one triangle inside it, and a quadrilateral will have two. A pentagon will have five ways to have itself triangulated, and a hexagon has fairly many. I guess it's 14. So this is the second case where Catalan number comes in. How is it related to Catalan number? What exactly is Catalan number? We will come to that, but I'm just making you aware. Um, I'm just showing you how where does it, in which cases it comes, and how these cases are related. Like I will be showing how there will be one-to-one correspondence between each of these scenarios, and by that I mean that for every element in first scenario, there is a corresponding thing that's just that just pairs up with the another scenario. That it's kind of like relating every element in either of the scenarios. Okay. So the next one is interesting. How many ways are there to create a mountain range? Um. Okay. So suppose n is equal to 0, where you don't have any pair of sticks. So n is equal to 2, where you have two pairs of sticks. So you can either go up or you can go down, but you cannot go underground. So you can do up, down, or you can go like up, down, down. So you can create mountain range by two ways. When you have three pairs of up and down, then you can go like U, D, U, D, U, D, U, D, U, U, D, D, and so on. So there are 5 ways to create a mountain range when you have three pairs of this. Um, so this is also a case where the Catalan numbers comes in. So the next scenario is like I guess we call it um I just can't remember the name, the term, but this scenario is like the parenthesis cases where we have 3 or maybe 4 numbers, and we have to kind of uh, write it down in a way so that we can multiply them. I mean, suppose you can't just know how to multiply 3 numbers simultaneously, then how can you multiply n numbers? So that like how many ways can you divide the process of multiplying n numbers such that you can only multiply 2 numbers at once? So this is the case that's also the case where Catalan numbers pops up. Now, I think Akash will be showing you um, how exactly um, the handshaking problem is related to Catalan numbers. But before that, I think I should show you the one-to-one correspondence between the bank transaction problems and parenthesis case. So I just want to ask you guys, did you have any questions while I was presenting the handshaking problem, or, or the sorry, I haven't presented the handshaking case. So did you have any confusion when I was presenting the bank transaction and consistency problem? I think maybe Abhishek can ask or Binod can ask. Dheeraj, did you get any? Did you have any question? Janak, any question?
I know that's the question.
Security, is everything all right? Are you getting everything? I guess you are,
Yes,
right?
sir.
Please don't call me sir. You can call me brother. Lah. Okay, so let's move on. All right. So where are you, Srikirti? You must be from Nepal, right? Where are you from?
Yes, brother.
Okay, okay, okay. Right. Um, so while we were discussing the bank transaction,
I'm from Nepal.
I didn't get you. Could you please repeat that? Excuse me, was it Srikirti or somebody else? Okay, I think. Okay. I think she might type that question. Okay. Um. Okay. So let's move on. So while I was presenting the bank transaction and consistency scenario, I guess all of you got that. The question was to arrange all the elements in the all the people in the queue such that bank is transaction at each of the transaction. Now, what is the condition over here in this scenario? At each point, the number of deposits is greater than or equal to the number of borrowers that has happened up until now. So it is the same case like bracket case. I'm sorry. Uh, so in this case, I'm so sorry for the interruption. So in this case of parenthesis also, the condition is that the number of opening of the bracket is same as the number of, oh sorry, the number of opening of the bracket is greater than or equal to the number of closing of the bracket. So at any point in while writing down the brackets, you won't be having more closing than the opening of the bracket. Let me show this through video. I guess you can see. Uh, so at any of the point, you won't be having more closing than you have opening, right? And also in the bank scenario, you won't be having more borrowing than you have deposits, like because the bank can't give money more than.
So are we assuming that the borrowed money and deposit money have the same quantity?
Yes. Yes, I mentioned it in the earlier that if we are going to assume that we have different sum of deposits and borrow, then the problem becomes fairly complex to discuss in this session. So um So that's the reason we might discuss it in the Discord, right? We regularly have, you know, chats over Discord. So we will provide you the social links at the end. So be there. So be with us up until the end. But yes, we won't be discussing the general case. Okay. I guess that's the unsolved problem. I'm not sure, but I have heard about that. So I guess you can see the one-to-one correspondence between the parenthesis cases and the bank transaction cases. So I think Akash should be presenting his his part.
Okay, so my part is straightforward. Into detail, I will just hand over the platform to Suyash after I present my two cases. So I'll just share my screen. I'll just switch off my video. My laptop will freeze otherwise. Uh, is the screen visible?
Yeah, but you're but you're not very audible. It's not clear.
Is the screen visible? Visible?
Yeah.
Okay. So my two cases are handshake problem. And parenthesis, which Chandan has already explained before. Um, so let me first talk about handshake problem, although it is talked earlier also. So let us suppose, obviously, so let us suppose there are two n where n is number. Obviously, people will be natural number. Obviously, there won't be negative people or decimal people. So there will be. So we suppose there are two n. So why we took two n because we want each people to shake hands with one another, not one another, but like there is four people. So
Akash, we cannot hear you clearly.
uh, hello.
Yeah.
Okay. So what I mean by why I took 2n is because like suppose there are A, B, C, and D. What the case I want to do is I want to sit in a circular table. Although this does not look like circular, but I want to see. I want them to sit in a circular table. So suppose A is there, B is here, C is here, D is here. So I want A and B to shake hands, and C and D to shake hands, or A and D to shake hands, A and C to shake hands, or A and B to shake hands, such that their hands like their hands won't cross. Case is there such that there is where two and people are sitting here as I took four people, so and is equal to two. So there are four people, so it's equal to A.
Akash, your writing is disturbing your mic.
Wait a minute. Now, okay, last.
Okay, Bolali, yeah.
Okay.
Please walk through whatever you said.
Okay. So basically, the case is I'll just simplify it. So basically, the case is that I am taking two n people where n is natural number. Obviously, people will be obviously natural number. So I'm taking two n peoples. Why two n? Because I want each and every like I want a pair of handshakes. Basically, a pair of handshakes between the people. So I'm taking two n. Like if I choose odd number of people, then obviously there will be one person. Like suppose there is E person here. Obviously, he won't have a pair to shake his hands. No? So I'm choosing even number of people. So this is straightforward. Uh, so I'm just so let us suppose for n is equal to 2. No, n is equal to 3. N is equal to 2 is easy. So suppose there is n is equal to 3. For n is equal to 3 is equal case 1, there are 6 peoples. 2, 3, 4, 5, 6. I want each of them to shake hands with one. I want them to make a pair of handshakes such that their handshakes won't cross each other. By won't cross each other, meaning I want to mean I want to say is that like suppose suppose A and C will, although they are a pair of handshakes, but the handshake should not be such that B and D is also a pair of handshake, but the handshake should not be across. The handshake should not form across. It should be either A to B or C to D or something like that, so that there is not a cross between their handshake. Okay, I'm just elongating the simple things. I don't know why. It is straightforward. I'm just like elongating in an unnecessary way. So basically, I want them to make a pair of handshakes such that their hands won't cross with each other. So one way I can do is 1, 2, and this way and this way, and also I can do the next. I can do 1, 4, 2, 3. Yeah. So these are the only possible cases. So any questions till now? I'm just doing like I'm just like randomly making cases. All the cases for n is equal to 3. These are the only possible cases. So there are 5 cases for n is equal to 3. Uh, any problem till now? Hello. Hello.
Hello.
Yeah. Any
This
problem?
is not at all. Go on.
Okay. For n is equal to 3, there will be 5 cases. So for n is equal to 4, there will be 14 cases. For n is equal to 2, there will be 2 cases. For n is equal to 1, there will be 1 case. So this in the above in the previous cases Chandan mentioned, for n is equal to 1 also there will be 1 cases. For n is equal to 2 also there will be 2 cases. For n is equal to 3 also there will be 5 cases. For n is equal to 4 also there will be 14 cases. So there are many cases also. So
There's a question in the chat, Akash. Please look at it.
which question in the chat?
There's a question asking if there are more cases, as in if 2 people can shake.
When we have one pair or 2 people in a table, then there is only one way to shake, that those two will be shaking their hands. We can't have
Uh,
other cases. I think I'm not sure
the
if
thing is,
the if the attendee is trying to ask something else, but I think
can you
this answer suffice.
can you unmute and ask? I'm not able to. Oh yeah.
No. All one people can't handshake with all of the other five. Like they will be simultaneously shaking hands. So at one point of time, one will be shaking hands with a particular one, maybe two, maybe person number two, and three will be shaking hand with maybe person number four, and so on. Like one person can't have other other five hands, like an alien who could shake hands with other five people simultaneously. That's not the scenario we are discussing right now, but
Yeah,
that could be possible.
yeah. This is a simultaneous case, and only one of your hands can shake. Obviously, you have two pair of arms, but you can only shake with one pair of one arm, not two. And this should be simultaneous. And also, there is a restriction that the joining of arms of two persons should not cross each other. So this will be the maximum case available. You can try it if you can find another case.
I didn't know the restriction actually. Sorry.
Yeah, I actually forgot to do that. Like, I will just
But
write the restrictions. Okay. The IMO. Get it. Yeah, one second. Like, so the handshake should be simultaneous, and they should the hands should not cross each other when you have an overview, like overhead view. So when you are looking from above, so basically this is a view from above. So when you are looking from above, the hands should not cross each other. The pair of uh, the handshake should not be seen as if it is crossing each other. Okay, so that is the restriction which we have. So if we follow those restrictions, we will have only five cases. So I'm sorry that I did not mention the what restrictions earlier. Like
And I really appreciate that Niradhar, Sachin, Om has asked their questions. And if they could ask by turning on their mic, that would be appreciated as well. And if somebody else also have their queries, then you can, ask immediately. Like otherwise, the confusion will just jumble up.
so okay. So I also so now it is about parenthesis, parenthesizing or something like that. I don't know the proper pronunciation. So we will talk about parenthesizing. So all of you, although like you should remember this. Like for n is equal to 1, there is one case or one way. For n is equal to 2, there is two way. Or for n is equal to 3, there is five way. N is equal to 4, there is 14 way. You should remember this result, because this result does not just pop out in this case. It pop ups in many of the cases, and we will then relate it to a certain number called Catalan number, which Suyash will present the derivation and all, so that you can understand at last more in more detail. So about parenthesis. So for example, for if we take n is equal to 3 and we make a parenthesis, just like Chandan said, it is already explained by Chandan, so I'm not going into detail. So there will be five cases. So this will be first case. So this is the second case. So this is the third case. So this is the fourth case, and the fifth case is which case did I miss? That's it. Yep, I missed this. Close हुन्छ अनि त्यसपछि open close open. So this is the case parenthesis. So my task of this session was to show that there is a what one to one. There is a bijection between this case, the handshake problem, and the parenthesis problem. So basically, uh, I will show it which case has a bijection with each other. So basically, this is equivalent to like this. So like if I if I suppose this bracket as something like say x, okay, and this facing as x and this facing as y, and if I suppose suppose there is a bug or something like that which starts from 1, and when like for it this will be the for example if this can for example when it sees it can when it sees a pair and it sees the first element of the pair. Suppose this 1 and 2 are making a pair. So this so when it encounters one of the first elements or one of the first substance of the pair, it will assign it as suppose up, and when it sees the second pair of the second element of the pair, it's assign it as down. So when we start from so for example, first I will just do it for this. It will be x y x x y y. So for this it will be up down from I will start from here. So up down, because this will be the first pair, so it will be up first pair, up down down. Up down up up down down. So you can see a so you can create a bijection between this and this. Any problem?
What if n is more than the given number?
Huh?
What if n is more than you are talking about?
Yeah, you can create that also for n is equal to 4 also. It's just that the case will be more.
Is it there any formula to?
Yeah, formula. Yeah, yeah. Formula will be there is a actually there will be a the formula for n is equal to 4, n is equal to 5, that can be given by a Catalan number formula which Suyash will derive. We're just giving an example that which shows that for such that there is a sequence n is equal to for n is equal to 1 there is 1 case, n is equal to 2 there is 2 case, n is equal to 3 there is 5 case, n is equal to 4 there is 14 case. We are just showing that we're just illustrating that this sequence arrives in many problems. For example, this problem in this parenthesis problem also it occurred, in handshake problem also it occurred, and there is like if you just like do a rough work and put in all the cases for n is equal to 14, you can also get a bijection like this for n is equal to 4 also. So for how to derive how do we know that for n is equal to 14 there is 14 cases, n is equal to 3 there is 5 cases, n is equal to 5 there is something cases, n is equal to 6 there is something cases. That will be talked by Suyash in his derivation of lattice paths and Catalan number. I think he will do it shortly. For now, if you have any problem with this, is there any questions now?
दा हजुरले त्यो अप डाउन कसरी लेख्नु भएको फेरि एकपल्ट भन्दिनु न मैले बुझिन
नेपालीमा भन नेपालीमा भन्छ
हुन्छ
अप डाउन भनेको त हैन एउटा बक्स छ रे के हैन एउटा बक भन्दा नि मै छोरी हैन मैले त यहाँबाट स्टार्ट गरेर हैन अनि मैले यो दुईवटा पेयर छ नि त यो दुईवटा यो त पेयर हो 1 र 2 त पेयर हो हैन अनि पेयरको त्यो फर्स्ट मान्छेलाई देख्यो भने चाहिँ मैले अप भनेर चिचाउँछु रे क्या कराउँछु रे हैन अनि मैले 1 देखि स्टार्ट गरेपछि त मैले फर्स्टमा त अब यो 1 र 2 को पेयरको त यो फर्स्ट हो नि त हैन फर्स्ट एलिमेन्ट त्यो भएर अप भनेर कराए रे हैन अनि स्टोरी जाँदा यो 2 भेट्यो रे 2 त सेकेन्ड एलिमेन्ट हो त्यो भएर डाउन भनेर कराए रे अनि फेरि जाँदाखेरि 3 मा भेट्यो रे अनि 3 मा त मैले अप भनेर कराए नि त किनकि 3 र 6 को मा त्यो 3 त फर्स्ट एलिमेन्ट हो त्यो अप भनेर कराए रे हैन अनि त्यसपछि यो 4 र 5 कोमा यो 4 के हो फर्स्ट इलिमेन्ट हो, त्यही भएर मैले अप भनेर कराएँ। अनि 5 सेकेन्ड इलिमेन्ट हो, त्यही भएर डाउन भनेर कराएँ। अनि 6 पनि एउटा सेकेन्ड इलिमेन्ट हो, एउटा यो 3 र 6 पेयरको, अनि फेरि मैले डाउन भनेर कराएँ। अनि यसलाई तिमीले यसरी हेर्ने हो भने एउटा बाइजेक्सन देख्छौ कि हरेक एउटा एक्सको लागि यु छ अनि वाइको लागि डी छ।
Okay. So you guys can continue asking questions. There is no restriction over there. But one of the attendees has asked over what is the purpose of Catalan numbers or this topic. To be honest, I'm not sure what exact is uses of Catalan numbers that we have, in advanced maths. But in this session, we are not just talking about Catalan numbers. We are talking about bijections, like one-to-one correspondence, and like finding one-to-one correspondence between different scenarios is the crucial idea of any combinatorial problem. And combinatorics comes up in daily life quite a bit. So I guess that 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 answers the query. I think you can Google or you may ask it over this Math Stack Exchange. What is the use of Catalan numbers specifically? Okay, so and also one of the pal had asked, how would you calculate Catalan numbers? I mean, it's represented by Cn, where n stands for, like, n is the number, could be anything like 5, 6, 7, or 8. So how would you calculate C8 or C9? Um, just by, you can't uh, think of all the arrangements of, the parentheses or the people being arranged in a queue. So what is there an algorithm or a formula? Yes, there is. But let me present you sorry. Okay, let me present you um, an algorithm that could be used to find Cn for higher numbers. And again, if you guys have any query, I don't know what background, I mean, what educational level you are in, but I will try to answer all of the questions that you have. I will do if I know the answer, and you guys just feel free to ask any of the confusion that you have. Okay, so all of you, I can, you are, so you just can simply ask. Okay, so let me turn on the video. Okay, so I don't know if you guys can see or not, but I'll try to write it bigger so you guys see. So the Catalan numbers are defined to be the Catalan numbers are defined to be the number of ways we can. Or could you please mute? I'm not sure who. Oh, thanks. The Catalan numbers are the number of ways to arrange parentheses such that it is a valid arrangement. We had talked about it. So how many ways are there to arrange these parentheses or brackets? Let's call it in short. Guys, please, it's embarrassing. I, for you, I think. I hope you guys muted me. So okay, and suppose you have 7 pairs, or maybe any number of pairs of brackets, and you guys have to arrange these so that it is a valid arrangement. And what valid arrangements we have talked about earlier. So in any arrangement, what is obvious? Like the first term is going to be an opening bracket, right? Okay, so since we have an opening bracket, there will be a corresponding closing bracket somewhere in the row. So these two things are obvious. Where it is exactly, we specifically don't know. but we do know that there is something over here and we know that something is over here. So how many ways are there to put the remaining n minus 1 bracket pairs in these two places? That's the number of ways we can arrange, we can put together n brackets. So what we have to do is arrange n pairs of brackets, and what we have done right now is break that problem to place n minus 1 pairs into these two places. So how many ways are there to place these n minus 1 bracket pairs over here? That's the Catalan nth Catalan number, right? So so if so suppose we put k of them, we put k of the pairs over here, and then we are left with n minus 1 minus k pairs. So we have to put k bracket pairs over here. So you are kind of like arranging k brackets pair. So you have ck ways, where ck represents the kth Catalan number. The way of arranging k brackets. Makes sense, right? And you guys have to arrange n minus 1 minus k bracket pairs over this segment. So it's a case like this and like this. So here we have arranged 3 brackets over here and 2 brackets over here. So if you have to put k brackets over here and n minus 1 minus k brackets over here, then you have ck ways to do that, and you have c n minus 1 minus k ways, because there are n minus 1 minus k brackets to put over here. Makes sense, right? But see, like, let me present you a simple case. So suppose you have to find c5, then what you do is you have the opening bracket and its corresponding matching closing bracket. Now what you have to do is either to put 0 bracket over here and put all the 4 brackets over here. You can put one bracket over here. I'm sorry. Okay, I hope you guys see. You put one bracket over here in this segment, and put rest of the 3 brackets in this segment. You can put 2 over here, 2 over here, 3 here, 1 here, or 4 here, 0 over here. So what I mean to say is nth Catalan number is just putting all the cases where we have to arrange n brackets. Now, how many ways are there to put those brackets over here such that there are k pairs in this segment and n minus 1 minus k pairs in this part? So if you can fill this space in ck ways, and if you can fill this space in cn minus 1 case, then there are ck times cn minus 1 minus k ways. That is the people say it fundamental theorem, no, principle of counting for multiplication, I guess. So if you can, so what I said is, if you can fill this space in ck ways, and if you can fill this space in with brackets in c n minus 1 minus k ways, then the total number of filling either of both the spaces is ck times cn minus 1 case ways. So we have this this segment and this segment, and this pairs with this one. Now cn is either we can put 0 bracket here and n minus 1 bracket here. So 0 times cn minus 1. I'm sorry if you guys can see, but let me. So cn is nothing but c0 times cn minus 1, and we can just go on this like this until we get to cn minus 2 c1 plus cn c0. And this is just all the ways that we can fill these two spaces. Okay, make sense? If you have any question and from any of the point, like it may be from the beginning of the part, we will try to answer. I know we are in short of time, but you guys can always ask. Yes, it should be n-1. Thanks. Thank you for correcting. I feel that I actually somebody's listening, and I'm not just telling and no one's listening to it. Okay, so if you guys have any question, you guys can ask. Otherwise, Suyash, I think you should start.
All right, I'll be starting my presentation in a few seconds, 30 seconds. So sorry for the delay, guys. Let me quickly share my screen. And hi, can everyone see my screen? And am I properly audible?
Yep, you are.
All right, cool. All right, hi everyone. I'm Suyash. I'll be giving a short presentation on Catalan numbers. Just as a few caveats, please don't ask me questions in between my presentation. I'll try my best to answer the questions that you have dropped in the chats after I finish my presentation. And two, this presentation will be a bit more intricate in terms of mathematical details. So this presentation assumes that you've got a fair knowledge of combinatorics, that is to say permutation, combination, what symbols mean, the number of ways of arranging something, number of ways of choosing something, and things as such. So with those out of the way, I think I'll be moving on to the topics that I'll be discussing in this session. I'll be doing three things. First, I'll be discussing about bijections, what they are and how they play out in this entire picture of Catalan numbers. Second, I'll be deriving an expression to generalize Catalan numbers as a whole. And thirdly, I'll be solving, or at least I'll be providing a solution to a fairly complex looking problem of combinatorics using the techniques that we discuss in this particular session. And lastly, I'll be leaving this floor open to discussions and I'll try my best to answer your questions. Bijections, what they are and how they blend in this entire picture. What are bijections? If we are given two sets, a bijection is a map from the first set to the second set, which is both injective and surjective. What does this mean? It means that no two elements of A get mapped to the same element in B, and every element in B is mapped with a particular element in A. So this picture exemplifies this entire concept perfectly. There's a one-to-one correspondence between elements, and bijection is also called one-to-one correspondence. All right, with the fair basic knowledge out of the way, we'll be using this concept to solve a particular problem, just as an example. The problem reads, determine the number of ways to walk from 0, 0 to mn, allowing only unit steps up or to the right. Now this problem, there are a few, it sounds tricky at first. It's really easy to understand and it's really easy to visualize as well. You've got this grid and you have got two rules. You can move either one step right or one step up, and you have to reach from one particular point to another particular point, right? Fairly basic. But then the problem arises when you have to frame this in such a manner that it's possible to solve this using mathematical formulae, right? And so to tackle this problem, you have to know one particular trick, right? In fact, there are many ways of doing this, many ways of solving this problem, but there's one particularly easy solution or one particularly easy trick that makes this entire process much more simpler, right? What's the trick? It's encoding the right steps as capital R or any letter of your preference and the up steps as U. When we do this, what happens? All right, let me exemplify this. you've got a grid, and I've randomly selected a particular path. This point, the bottom left point, is 0, 0, and the top right point is MN. And so this is a random path, this one in bold, which I selected. And so when we apply the previous trick, what happens, this is this entire path, which is a graph. I'm really sorry for the disturbance, guys. This entire visual graph gets translated into a bit more mathematical form. That is to mean this translates as RR, 2 right steps, U, then RR, 2 right steps, 2 up steps, 2 right steps, 1 up step, 2 right steps, 3 up steps, 2 right steps, and 1 up step. So this the thing in the bottom is the encoded translation of this visual graph. Why is this important in this particular problem? There are a few things to note before knowing that. First, the total number of right steps that you take is M, right? Because in this problem, you don't move diagonally. The only way that you move towards right, towards M, is through taking unit right steps. So it's fairly intuitive that the total number of right steps that you take is M, right? With the same logic, the total number of up steps that you take is N. So which in the end implies that the total number of steps that you are taking in this entire process is M plus N, right? Now with these things in mind, we will go to a bit more details, a bit more intricate details about this problem, right? So those things imply that in our encoded translation, and I've mentioned this before, there will be exactly MRs and exactly NUs, right? This further implies that there exists a bijection between the set of walks from 0, 0 to MN using only up steps or right steps, and the set of sequences consisting of M copies of R and N copies of U, right? So this is a fairly intuitive bijection as well, right? Because for each particular path, you've got a unique translation using the trick that I had mentioned before, right? So with this out of the way, we can now move on to the mathematical part of this entire problem, right? Now we know how to count the latter set. That is to say, the set of sequences consisting of M copies of R and N copies of U, right? Mathematically, that is equal to choosing N R's or N U's or M R's from the set of M plus N R's and U's, which translates as choosing M plus N choose N, right? Fairly easy stuff. And that's our answer for this entire problem, right? There we go. With that out of the way, now we'll move on to deriving the expression for Catalan numbers. And you have to know this entire concept of bijection to know how this expression is derived. And this is the particular expression that we'll be deriving. So bear with me for a while. To derive this, we'll be solving a problem. The problem reads, let n be a positive integer. We have to determine the number of lattice paths, which is to say the paths in the grid from 0, 0 to mn, not mn. Both x and y should be equal in this case, using only up steps and right steps, such that the path stays in the region x is greater than or equal to y, right? So we are introducing two constraints in this problem. First, the path must stay between that diagonal axis or diagonal line that we draw from 0, 0 to nn. And second, the grid should be a square, right? Because this statement implies that. Now, this problem is a bit complex than the one we discussed before. Why? We previously saw that the total number of lattice paths from 0, 0 to nn without is C2nn. It was choosing m plus n elements from m plus n elements. In this case, m and n are both equal, so it's 2n choose n. And so we have to now count the paths that go. So We'll tackle this problem not by directly counting the number of good paths, which I'll be explaining what good paths are in a few seconds. But what we'll be doing is we know the total number of paths from 0, 0 to n using up steps and right steps. And so if we find that the total number of paths that go into the bad region, that is to say that the region above the diagonal axis, then we can subtract both of those. We can subtract the number of bad paths from the total number of paths to obtain the number of good paths, right? Fairly easy. Let us suppose that there exists a particular path, P, which is a bad path, right? Just a few seconds, guys. I'm really sorry for the disturbance. All right. Let us assume that there exists a particular path, P, which is a bad path. That is to mean it does not stay under that axis, under the axis greater than or equal to y region. It moves out of that region. And so if it does that, since the only permissible step that we can take is one step at a time, it must hit this line, y equals x plus 1 at some point, right? In this picture, P is a bad path. It crosses this axis and it hits this line, y is equal to x plus 1 at a point x, right? When that happens, what we do is we reflect the portion of P that does not hit that particular line. That is to say, the portion of P that is inherently good about the axis of y equals x plus 1. And this gives us a new path called P prime, which I've highlighted here. What this does is this gives us a bijection between the set of bad paths to the set of lattice paths from -1, 1 to n using only up steps and right unit steps. Guys, I know that this sounds really complicated, and it's really difficult to see the bridging between how we went from reflecting this entire thing about a particular axis and directly formulating a bijection between those things. But when you ponder on this for a bit, you can see that these things are quite intuitive. Why? Because once we reflect this about y equals x plus 1 path, the starting point translates to -1, 1. And every path and the paths that you are taking from here to n come to become bad paths. That is to mean that come to become some paths which may not be bad, but then they are paths which are from -1 to n, -1, 1 to n. Those are basically set of every possible path from -1, 1 to n, right? Now this sounds a little bit complicated, and I know I too was once in this particular stage, but I request you guys to ponder on this thing for a while, and I'll be making these slides available in the MIN's messenger chat or in the Facebook page. And so look at these things, and these will come out to be fairly intuitive. So once we've formulated this bijection, we know how to count the latter set, right? That is to say, the set of lattice paths from -1, 1 to n using only up and right steps, right? So the total number of bad paths, and this is fairly easy stuff, and we are counting the ladder set, and the ladder set comes out to be 2n, n plus 1. 2n, choose n plus 1, n, right? Why is this the case? That is because, look at this picture. The x number of steps that we will be taking is n plus 1. So we'll be choosing the same logic from the first problem. We'll be choosing n plus 1 elements or n plus 1 r's or u's from this entire set of 2n permissible elements. And so when that happens, we get this particular result. And so by the thing that I'd mentioned before starting this entire derivation, the total number of good parts come out to be the total number of parts minus the total number of bad parts, which by some computation comes out to be 1 by n plus 1 to n choose n. Easy stuff, and the expression for Catalan numbers. With that out of the way, there we go. We have just computed the expression for Catalan numbers. Voila. Now, as a warm-up, and this problem has been discussed by the previous speakers, by Akash and by Chandan as well. And this is a really famous problem. The concepts that are used in this problem really help you a lot if you're thinking of pursuing Olympiad in the future or even now. The problem reads, show that the nth Catalan number counts the number of expressions containing n pairs of parentheses which are correctly matched. For example, for n equals 3, this is one permissible good parentheses arrangement. This is another one, this is another one, this is another one, and this is another one, right? So there are in total 5. And so 5 is the, I don't know, what was 5? I guess 5 was the n plus 1. 5 was the second Catalan number, I guess. I don't remember that stuff, but well, 5 is one of the Catalan numbers. Yep, it's the nth Catalan. 5 is the third Catalan number, I guess. So, all right. To solve this, we've got to find a bijection between the parentheses expressions and the lattice paths counted in the previous problem. If we interpret the left open parentheses as a unit right step and the right closing parentheses as a unit up step, we obtain the desired bijection. I won't be solving this problem totally, but this will come out to be, or at least result to be, a fairly intuitive solution if we just ponder on this for a while, right? So there is a small caveat. The condition that the parentheses expression is correctly matched corresponds exactly to the condition that the lattice path does not go to the x is less than y region, right? Why is this the case? Notice that for every right closing bracket, there occurs a left opening bracket already, right? That means that you can only have a up step after you have a right step. And so when you do this, it's fairly intuitive, or at least play with this for a while in your brain, and it becomes fairly intuitive that this entire path that is being formulated in this entire process in your brain lies under the x is greater than or equal to y region, right? And so when this happens, this forms a bijection between the Catalan numbers derivation that we just did and this problem, right? So what that further implies is that the total number of correctly matched parentheses and parentheses corresponds to the nth Catalan number, right? And there we go. Fairly basic solution. You have to play with it for a while in your brains. But once you do that, it becomes fairly intuitive and it becomes really easy to see, right? To visualize. And I guess that's about it for my presentation. Now, I know most of it was filled with jargons and stuff, but you have to play with these things for a while in solitude and it becomes really easy to see, right? As references, I used 3 particular ones. Most of it was from Yufei Zhao's Olympiad handouts. And look through these references once these slides are available, right? That's about it, I guess. If there are any questions or anything you would want me to discuss, I'll be looking at the chat right now.
this will be available in all of our social channels and our YouTube channel. The presentation would also be available in the same.
All right, cool. I see no questions. Thank you for tuning in, guys. Thank you. Please explain the graph again. Which one? This one? Or maybe this one?
यो वाला Suyash, यो वाला भनेको.
Just a sec. Let me quite out. All right, this one. This graph. All right. We have got a bad path. I'm assuming that you know at least what bad paths are based on my poor explanation. But bad paths are basically paths that hit this line, right? This line y is equal to x plus 1. And so if P is a bad path and it hits this line at a point x, then what we will do is we'll reflect this path, we'll reflect this particular path or about this axis, and we'll obtain a new path, P prime, right? And notice a few things about P prime, right? A, it starts from -1, 1, and B, it ends in n, n, and C, this path, or at least generalization of this entire path, is every permissible path from -1, 1 to n, n using only up steps and right steps, right? So if we had a path, let's say that went like this, right? Then after reflecting this, it will come out, the starting point will be -1, 1. Every graph that is reflected in this way will start from -1, 1. And it'll move accordingly. It'll move to n, n by using right steps and up steps. And what that results in is the total number of paths from -1, 1 to n, n, right? And so the total number of paths from -1, 1 to n, n is 2n, choose n plus 1, this one. And so the total number of good paths is this. Why? Because the total number of paths from -1, 1 to n, n and the total number of bad paths, those are bijected sets, right? That is to mean that every bad path has got a corresponding path from -1, 1 to n, n, right? So that's it. And you're simply subtracting those and you're obtaining the nth Catalan number. Was that clear, or should I explain something more? All right, so if you have mn, n instead of n, n, you won't obtain the desired Catalan number. You can still solve that problem and you can still come up with a result, but then that result may not necessarily be the general expression for obtaining the nth Catalan number. And that's solvable, but we are not discussing about that at this particular instant, since this session is solely focused on Catalan numbers. Is there anything else? All right, seeing none, I'll be concluding my presentation here. Thank you everyone for tuning in. Thank you, and hopefully go through this slide a bit more and try pondering on these things for a while, and hopefully everything will be clear. Thank you.
Prashant.
Okay. I guess that concludes today's session. I thank everybody for coming. And if you have any questions, you can always ask us in our email. You can email the questions to us And this video will be available in our YouTube channel, and the presentation Suyash told about will also be available in our socials. Links, I'll be putting the links in the chat. And if you have any suggestions or any feedback to give, please fill out this form as well. I'm leaving that in the chat as well. That's the form. And
Hello, brother.
these are our socials.
Yes, please.
Can we get the contact details of the presenters so we can contact further? If
You can
we are
always
going to-
email us. You can always send us a text to our Facebook page, or you can email us and we will get back to you.
I don't
Or
consent
you,
for my contact information to be public, Prashant.
Okay, I'll take that.
or you can ask your question through the Discord server, public Discord server of Mathematics Association of Nepal.
I have linked all our socials in the chat. Please go through them and join. And if you want to join our messenger group as well, send us a message to our Facebook page so we can add it to the group. Anyway, about Road to Olympiad. This was the second episode of our Road to Olympiad series. The next episode will probably be next Saturday or the Saturday after that one. And you will all please check your emails. We will be updating you on the Road to Olympiad sessions on Tuesdays or Thursdays and Fridays. So thank you everyone for coming to this session. I would like the MIN members to stay back, and everybody else, please. It was good. It was a good session for me. You may leave now.